generalize now to the multidimensional case. So instead of having just a single value, we now combine several samples into a vector and then quantize this vector. And this is what we'll see today with a vector quantizer. So remember with Log max quantization, we have this following iteration. We start with some random initialization. First, we assign the reconstruction values randomly to code words. So now it's many code words because we have vectors, more like a word, not just a sample. And then, using those reconstruction values, we can compute boundary values as the midpoint between two reconstruction values or code words. And this can also be generalized in terms of, instead of having just a value, we have now a boundary between two reconstruction values. And then the third step was using the PDF, the probability distribution of our signal, and the boundary values. We can compute new reconstruction values for code words like K as centroids over the quantization errors. So this is the conditional expectation of the centroid of the reconstruction error. So now we can repeat this until the update is sufficiently small, smaller than the sound desired as well. So this algorithm usually converges. Depends on the PDF, but usually it does convert, and it finds in this way an equilibrium which doesn't change anymore, and this results in the minimum distortion D. The minimum expected distortion. So it's interesting that this can be generalized to the multidimensional case, the so-called vector quantization. So in scalar quantization, we usually make the assumption that we have a memoryless system or signal, which means that one sample is more or less random or totally random. It does not have anything to do with its neighbors. But when you look at, for instance, speech or audio, they have a lot of similarity, so they have to do a lot with their neighbors. So indeed, this assumption of having no memory often is not quite true. So examples of no memories are, for instance, white noise, or a sequence of dice tosses or lottery numbers. So if you throw a dice, then the number you get is totally independent on the previous number you get. But when we look at signals like speech and audio, it's different. So we have memory, which means that you have statistical dependencies between neighboring samples. So when you mention the speech signals, or in general, pink noise, which means noise which has a non-flat spectrum, you can see it as white noise. Passed through a filter, and then this filter gives the sample memory. We have relationships among each other, and that's because our impulse response has memory. Or temperature values over the year, or image signals, or audio signals. So they all have dependencies between neighboring samples. So since many signals of interest indeed have memory, this suggests that we can do a better job in quantizing. So one possible approach to deal with memory or statistical dependencies in our signal is to use the so-called vector quantization. And a possible reference for this is introduction to data compression and the section about vector quantization by Sayuri. Be able to get into that. So how does vector quantization work? Instead of quantizing each scalar value or each sample individually, we first group the sequence of samples into groups of random samples. So we put them into blocks of n samples, which you can see here. So this is the first vector, the first block of n samples, then you have the second block, and so on. So you have a sequence of blocks or sequence of vectors, n-dimensional vectors. Yeah. So in this way, we obtain a sequence of samples in an n-dimensional space. So imagine we have 3 samples, then we want to have a point in 3-dimensional space for each of those vectors. Yeah, in such a way we can capture or use the memory between the samples of each block or vector, because then the resulting sample in the higher dimensional space will lie in the hyperplane. They will have a pattern in this higher dimensional space. Yeah, so the resulting samples with memory in the n-dimensional space will lie on or near the hyperplane or subspace within this n-dimensional space. So that means we don't need to sample the entire space, but we only need to sample the part of the space where our sample actually are located, which might be much less. And this is actually what gives us savings in bit rate or reduced distortions. We concentrate our sampling points on those hyperplanes and they are more closely together, which means less distortion. So for example, we can take correlated samples, such that one sample is always similar to the previous sample, just like in the sample of speech or audio samples. Usually we don't have very high frequencies there, and that means the curve through samples is more or less smooth. Right? When you think of speech, usually they're not very high frequencies. So in our example, we now take the dimension n equals 2, which is probably not enough to take advantage of the memory, but it's easy to plot here on the board. So that's I'm taking this 2-dimensional example. So we just take sequences of pairs, first pair, second pair, and so on. And that means each of those 2-dimensional vectors is a point on the surface, and then we can plot it. So for instance, you might have this sequence of samples, some more or less random vectors, values I took here, and then we group each 2 into a vector. So now we have a sequence of 2-dimensional vectors, just by grouping them into blocks of 2. Yeah, and each of those vectors can now be represented as a point in this 2-dimensional space. So here is the first sample of each vector, and this is the second sample of each vector. And that means each vector is one of those crosses here. And if they are similar, they lie on more or less this diagonal here. Make sense? Mm-hmm. So we can also try a Python example where we actually try a speech signal. As I did here. So we use IPython. Everybody knows how to use IPython? Okay. So here we use IPython, and we use the scipy.io WAV file library as WAV to read in a speech file, which we do here on the next line. WAV read mspeech.wav. This is our signal as an array, and rate contains the sampling rate as an integer. And we just take an extract of 1,000 samples, starting at sample number 2001, and plot it. So here, speech example is our sound array. I'm starting at 2000, and then I'm taking the next 1,000 samples. NPR gives us the next 1,000 samples. Make sense here? Yeah. So now we can plot it. So we will see the example. So this is a typical short snippet of which is the speech waveform. So you can see here 0, so it's plus and minus, but you can see neighboring samples actually have a lot of similarity even here. So they are not very different. So now we can actually take two-dimensional vectors by grouping them into pairs of two. And then we can plot the even indices on the x-axis and the odd indices on the y-axis, so that we have a point for each of those vectors. And here you can see it. Here's the x-axis in the plot. The first argument is the x-axis, second argument is the y-axis. And then for each point I'm using the plus sign to plot it. So here I'm starting with 2 as an even index, and I jump in steps of 2 until the end. Here I'm starting at 1 as the odd indices, also in steps of 2. So here I'm getting the odd indices, here I'm getting the even indices. So, and then each vector is then a plus. And you can see the result here in the following plot. And you can see here is indeed very much on this diagonal hyperplane. So here you can see this is the center, 0, 0. And it's all very nicely on this diagonal. Okay. So there's not much going on here and here. It's pretty much empty here. So if you want to quantize those speech samples, it makes sense to concentrate on this area here. You don't want to waste any quantization intervals here and here. You can make those intervals very big. Maybe have one representative here and one here, and then the rest is finely distributed here. Then we have very low quantization of this. Yeah, so indeed we get a distribution of vector points near the diagonal of this space. Right? So that means you also need to sample the space only near this diagonal. Or more generally speaking, we should sample more densely near this diagonal. So we can have coarse sampling of our space outside this diagonal, fine sampling where we have all those points. Yeah, so this shows that we need few reconstruction values or cohorts as in the one-dimensional case, which means fewer indices for them, and hence fewer bits for the quantized signal. So we can have either finer resolution or fewer bits. Yeah, so for the vector encoder, we get a division of our signal into signal vectors, and then it finds the nearest code word, and then transmit the index of this code word to the decoder. And in the decoder, it reads out the code vector from the code book using the index from the encoder. So the decoder gets the index, looks up the corresponding code words, and then just concatenates the sequence of code word vectors into a sample stream. So then we are back from vectors to samples. Yeah, an interesting point here is that vector quantizers not only give an advantage for signals with memory, but also even for signals without memory. In the scalar case, we can only sample an n-dimensional space on a regular grid, which is given by the coordinate axis of the space, whereas with the vector quantizer, we can use something like a densest sphere package in this n-dimensional space, such that we reduce the distance between reconstruction vectors, the so-called code words, and hence reduce the expectation of the quantization error in this case. So imagine you have like balls and pack them together. Then it's not like they are regular on top of each other, but the next layer is like in between the previous layer. And this is what you can do with vector quantization. So this can be seen in this next picture. So here you have those balls, which is basically our quantization intervals in 2D. And here you have the code vectors the center. And if you have a one-dimensional quantizer, then all you can do is use this regular grid. This is the same for each, or it's uniform for each axis. But now if you go to the 2D case, we can pack those circles closer together such that the next layer is in the gaps of the previous layers. And this way you have finer quantization. Yeah, so in this way we get a denser packing, shifting the spheres in the gaps of the neighboring layers, which results in a reduced reconstruction area. Yeah, so how do we do the quantization in the n-dimensional case in general? Right? Not just two-dimensional, but n-dimensional. We choose n-dimensional reconstruction values, which we now call code words. We use the nearest neighbor rule to map each n-dimensional signal vector to the nearest code vector. So remember, we can still do that in n dimensions because we have a distance measure. So when we have a vector and we have a set of code words, then we can compute the distance between the two. Do you know how to do it? You can, for instance, take the Euclidean distance, right? Which is you just take each dimension, square it, add them all up, and then take the square root. We can also omit the square root because we're just interested in the smallest one. Yeah, and once we did that, we just choose the code vector which has the smallest distance to our observed signal vector. Right? And that's then our representative. Yeah, so in this way we can easily generalize this nearest neighbor rule to n dimensions. Yeah, so you could think of the neighborhood as an n-dimensional sphere around each code vector. Each code vector has an index, and this index is then transmitted to the receiver, which uses this code vector as a reconstruction value. The collection of all code words is called a code book. The size of the code book also determines how many bits are needed for the index. The more code words we have, the longer the index needs to be. Usually code books are fixed and predefined, but there are also adaptive code books, for instance, in speech coding. So in speech coding, usually you have one part which is fixed, and then you have another part which is adaptive. Yeah, so how do we obtain our code book? Or our code vectors? It's basically like in the Lloyd Max case, where we're just extending the n-dimensional case. For the n-dimensional case, this is called the Lindenbusum-Gray algorithm, LBG. You can also read about it in this book about Introduction to Data Compression. So basically it looks very similar to Max Lloyd. So we have some initialization with random n-dimensional code words, like K. We don't need to start with random code words, but that's really the easiest case. If you have a better case, that's fine too. So then the second step, using these code words, you can compute the so-called decision boundaries BK. Right? So these BKs are not just numbers anymore, but they're lines between or hyperplanes that divide the regions of neighboring code words. And here this bold phase indicates that it's a line or hyperplane. So this is basically the set of all points with equal distance between two reconstruction values or code words. Such constructed regions are also called Voronoi regions. So the region around each code word, which belongs to this code word, is called Voronoi region. And this is using the nearest neighbor. So you imagine you have like kingdoms, and you have a king in the center, and then the kings divide their kingdom such that the borders are right in the middle between them. Yeah, so to assign a vector to a specific region, we use the nearest neighbor rule directly. We simply test which code word is closest to the observed vector. So once we then have those Voronoi regions, we can then recompute the code words as the new centroids or center of mass using the conditional expectation over the quantization errors or the Voronoi region. So in the first step we have our random assignment, then we create our borders, and once we have our borders we can now compute the new centroids given the signal. And each Voronoi region has a certain amount of signal vectors falling into them, and then we can compute the new centroids. And the new centroids are the new reconstruction areas or the new code words. Yeah, so this is the same as in the one-dimensional case, just here the integral is going over n dimensions. Yeah, and then we repeat this until the update is sufficiently small. And this is then the ADG. Yeah, so here we assume we have a PDF of the signal, the probability density function. But observe that here we would need a multidimensional PDF or probability distribution, which is in general difficult to obtain since the volume of the space increases exponentially with its dimension, but the number of vectors rather decreases. So that's the problem. We have only a coarse sampling of our n-dimensional space. So we get less points in the high-dimensional space, which means the PDF is difficult to estimate. So that's in general the problem that we have with high-dimensional spaces. So hence, instead of a multi-dimensional PDF, we often only take a so-called training set to obtain our codebook. And that's the usual approach. Usually we don't have an n-dimensional PDF, but we have a training set which contains our typical signals. For instance, if you want to quantize speech, then we have a training set of typical speech signals. Yeah, so the training set is a set of signals which have statistics like our targeted signals, like speech. Yeah.
So you are talking about that we should have a training set. So in between, so we will have some neural networks, right? To neural network for training and all.
No neural network, right? This is the name is also used in neural networks, but here we are not talking about a neural network. Right? We just have, say, many recordings of speech. Female speech, male speech, speaker who is saying different things, different persons talking. And this is a collection of speech signals which you use to obtain speech statistics, basically to get the code word. But the approach is very similar to neural networks. Right? In neural networks, you have the same approach. You have a training set where you have signals where you want to, for instance, recognize something or classify somehow, and then you have a target set, which is the desired outcome. So here we don't have a target. Right? No target set. All we have is a training set, and the output here is our code book. Yeah, but in a way it's also kind of a ruin. Right? It trains the code book. And in this sense, it also has similarity with neural networks. Neural networks adapt to a training set, and here the code book adapts to the training set. Right, so we use this only to train our code book, and then we have a test set to test it. So this is also like neural networks. In neural networks, you also have a test set to test it. And this test set should be different from the training set to avoid overfitting. Yeah. So we should use signals which are not in the training set. Also called test set. Yeah, and the approach now to compute the centroid is slightly different. Since we have a training set instead of the PDF, we have to modify the computation of the centroid or the conditional expectation accordingly. So assume we have L samples in our Voronoi neighborhood region and want to compute the centroid of this Voronoi region. We could do that by assigning each signal vector x of k of the training set to a probability of 1 over L. We assume each vector is equally likely. So this is just an assumption that we can work with. It's a working assumption. And then just use the above formula for the centroid, replacing the integrals by the sums, because now we have discrete points in the n-dimensional space. And this results then in this equation. So this is our conditional expectation here, the sum over all the x divided by the number of signal vectors here. And this basically gives us the new code vector. So number of signal vectors in this Voronoi region. And here we have the sum over the vectors inside this Voronoi region. Makes sense? So basically, again, this is the average of the signal in our region. So this is basically the same as the probability of, or the expected value in this region, given that the signal is in this region that we had in Noise Max. So here, this gives us the new expected value or the new centroid. And you can see the computation is fairly easy. It's just the average of those vectors. Yeah, so the sum contains the indices of signal vectors xi, which are closest to the code vector k. Yeah, and then after training the corpus with the training set, only for training or learning to obtain the corpus, we have a fixed corpus, which we can then use for encoding our data. Observe that the training set should be different from our data, and which in general is. So before we have our code vector, the code book, we train it, and then we use it for, say, encoding speech in the telephone network. So the resulting vector quantizer could look like in the following image for dimension n equals 2, where the blue lines are the boundary for the Voronoi regions, consisting of our bk, and the red stars are the code vectors yk, and the green dots the signal vectors. So this is now a graphical illustration. Here you can see the example. So here you can see the blue lines are the boundaries of our Voronoi regions. Okay, so each of those blocks is a Voronoi region. And then those stars here, the red stars, are the code vectors. And those green dots are the signal vectors. Make sense? So you can see that when you look at these green dots, then the red star is really like the centroid of those green dots in each region. So you can see it's like in the center of all those dots in each region. Yeah, and picture is on this page. Yeah, now an example. We want to determine the codebook of vectors of an AVG vector quantizer for dimension n equals 2, and the number of code vectors should be n equals 2, so just 2 vectors. After one iteration for 2 vectors with a given training set x, and this is your sequence of samples, so it's a toy example. So the initial codebook vectors are just some random vectors. Here 1, 2, y2 is 5, 6. It's just some initialization. And the training set vectors are hence the groups of 2, the blocks of 2 from the signal here, which you can see here. So this is your training set. And then the solution follows variablism, which was explained above, basically. So we already have our randomly assigned codebook vectors. The next step is to calculate decision boundaries BK using the nearest neighbor rule. So this results in a set of midpoints, and these midpoints then form the Voronoi boundary line, which is perpendicular to the connecting line of the 2 codebooks. So here, the big midpoint in this case would be just the middle between the 2. So observe that in the higher dimensional case, you wouldn't really compute this division line. You would just compute which signal vector comes closest to which codebook vector, without explicitly computing this boundary line. So VK in our case is the line going through the points 3, 4, the line consisting of all points which have equal distance to the neighboring code vectors. So now we can draw the given training set vectors, codebook vectors, and the Voronoi boundaries. Observe that the computation of the boundary line of the midpoints is useful only for drawing this picture, but in the computation implementation we don't need to compute it, but use the nearest neighbor rule directly. Basically just for drawing. So here you can see the resulting picture. So we start with YKs. Here, these are our randomly assigned codebook vectors, and the green dots are our signal points, the signal vectors. So now we just take the midpoint between our 2 code words, here's the midpoint, and we draw this perpendicular line. And this gives us now 2 Voronoi regions. Number 1, number 2. And these regions divide up also our signal vectors. So here there's only one left in the region 1, and we have 3 left in region 2. So now we can update our code words. So which would be our new code words? Say in this region, what's our new code word in Voronoi region 1? Yeah, but we need to update it, right? So how do we update it? Any idea? Remember the rule for updating the code vectors? We can go back to this rule. Yeah. So the new code vector is basically the average of the signal vectors falling in its Voronoi region. So we need to take all vectors which fall into this Voronoi region, all signal vectors, and compute the average. So going back to our example, so here, what's the average of all signal vectors which fall into this Voronoi region 1?
We have only one, so it's that one. We don't have to compute the average.
Exactly. Does everybody see it?
Yeah.
So we only have this one signal vector here, and the average over this one signal vector is this signal vector. Right? So basically that means we move this code vector to this point. So this is very easy. We don't even need to compute anything. So what about those three in this Voronoi region 2? How do we update this code vector? Any idea roughly where it will go?
Between 7 and
Somewhere here?
between 7 and 8.
7 and 8.
No, yeah. No, a little lower.
Yeah.
Lower, a little lower, yeah.
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 What do you think? So basically it should be the average between those three
Yes.
signal points, right? Yeah, I guess it's somewhere
Yeah.
here. Right? You see that? So that's what we did here. So we compute the code words using this average over the Voronoi region. Yeah, so in order to find in which Voronoi region the vector is located, we use the nearest neighbor rule. So if you don't have this graph, you have to use the nearest neighbor rule. For that, you need to calculate the Euclidean distances between all the training set vectors and codebook vectors, and then decide which training vectors are closer to which codebook vectors. For each training set vector, we compute to which codebook vector it has the closest distance with the Euclidean distances calculated in the following way. So you can see it here. So this is now how you would actually do it in a computer. For each training set vector, you compute the distances to the two code words, or to all code words. Right here we just have two code words, so that makes it easy for this example. But in general, in your computer doesn't mind if you have, for instance, hundreds. So here you simply compute the Euclidean distance between x1 and y1, and you can see here it takes, for each dimension it takes the difference, squares it, then sums it up, and takes the square root. Okay. So here the distance to code word 1 is square root of 4. Here we see the distance to code word 2 is square root of 20. So code word 1 is the closest. For signal vector 2, distance 1 is square root of 18, distance 2 is square root of 2. So this is the closest. In this case, 2 is the closest. So then you continue with the next two. For signal vector 3, you can see D2 is closest, so Y2 is closest. So code word 2 is the closest. For the last one, you see here D2 is smaller, so Y2 is closer. Make sense? So in this way we know in which Voronoi region each signal vector is. So now we can compute the centroid of condition expectation for each of the two Voronoi regions. So Voronoi region 1 only contains training set vector x1. Hence the centroid is x1, and that means y1 becomes x1. This is what we just saw. So for Voronoi region 2, we have the remaining three vectors, and we obtain centroid by averaging over them, and obtain the true codebook vector 2 as this average. So we get 6 plus 1/3 and 7 plus 1/3. So this is the mean plus 1/3. So this is the mean codebook vector 2. So the updated codebook vectors will look like this. So we move the old codebook vector to the location of this training set vector, and we move here this location from here to here. So pretty much like we estimated. So now we is the centroid of those three points, the average of those three points. Yeah, and now we need to go back to the beginning and repeat the process until it doesn't change much anymore. So I stop here because it shows you the principle. In reality, we have to iterate a few more times. Yeah, so in an encoder and decoder setting, we would use vector quantization, where both encoder and decoder have the same codebook in their memory. So basically, you train on the training set, and if you design your system, both get the resulting codebook. You obtain the codebook from the training set, and this codebook then goes into memory. It's fixed. Encoder and decoder get the same codebook. In an encoder, we first convert our signal sample stream to our vectors, then we map those vectors to the nearest code vectors. We transmit the indices of those code vectors to the decoder, and the decoder then converts the indices back to code vectors. And in this way, we obtain the stream of sample data. The code vectors are then concatenated and converted back into a stream of samples. So this is what you can see here. An encoder converts the stream to vectors. For instance, these two vectors here, a sequence of vectors. And then the vectors to the code vectors. Here we obtain the nearest code vectors here. You see there is a difference. They are not exactly the same, and this is the quantization error that we made. We still have the quantization error. And these vectors now have indices. So instead of these values, we just transmit those indices, in this case 4 and 5. And these indices are usually much shorter than the vectors itself. Then in the decoder has the same codebook. It takes the indices in the table lookup, where the codebook is stored, and obtains these vectors. And then it just concatenates these vectors to get the reconstructed sequence of samples. Yeah, makes sense so far? So this is vector quantization, and vector quantization is actually used much more often than Max-Lloyd quantization. So Max-Lloyd is more like the first step towards vector quantization. So let's continue with the next set of slides. Yeah. So the question is, what if the samples don't fit exactly to the vectors? So what do you do?
Change those zeros.
Oh? Yeah, adding zeros might be a possibility. More ideas? Was something?
We can scale the axis, the jump between the axes.
No, you're given the samples. You cannot scale this. You have a certain number of samples, and at this point, you cannot change it anymore. Basically, you can change it when you do the sampling, which is the next topic. Right? You would change the sampling rate, then you could scale the x-axis. But usually, the sampling at this point is fixed, and you have to take the samples which are given. Well, you could just drop a few samples. In speech, it usually doesn't matter, nobody hears it. So these are the two possibilities. Drop samples that don't fit anymore, or add zeros. Good point. Yeah, so now to sampling. So this is about how to obtain our samples. About downsampling and upsampling. And first sampling the analog signal, which happens in our sound card. Or say microphone signal, and then the sound card converts it into a stream of samples. Yeah. So to see what happens when we sample a signal, let's start with the analog signal S of t. So t in this case is a continuous time variable. Sampling, it means to sample the signal at sample intervals capital T. For instance, 1/8000th of a second in the ISDN example, which means you get 8,000 samples per second, which is not very much. Or sampling frequency fs of 8 kilohertz for the ISDN example. So mathematically, sampling can be formulated as multiplying the analog signal with the Dirac impulse at the sampling time instances lowercase n, uppercase t, where n is the number of our sample, where n is 0, 1, and so on. It's an integer. So this would be the sequence of Dirac sequences, starting at 0, and at integer multiples of capital T. Does everybody remember what a Dirac pulse is? What's the integral over a Dirac pulse? Oh, very good. So the sequence of or train of Dirac impulses can be written as the following sum. So the data here is our Dirac impulse, and Dirac of t has the Dirac pulse at 0, t equals 0. And if you want to have a shifted Dirac pulse, you just subtract this shift t. So this would appear at position nt. And if you have the sum, we have many Diracs, each Dirac appearing at integer multiples of t. And remember that the integral over the Dirac is 1. This is important for sampling. So if we now take our analog signal S of t and multiply it with this Dirac pulse, in this case just one shifted Dirac pulse at position nt, then since the integral over this Dirac is 1, and the width is infinitely small, right, then all what's left of this integral is the value of s at position nt. Right? So in this way, we did our sampling. Which means here, this is our sampler. It sampled our signal at position nt. So So mathematically, very easy to formulate sampling this way. In reality, it's a little different. We have basically a gate which closes quickly, and then we have a value. But that's basically what this formula is doing. Yeah, so we have the sampling at sample at point NT, and we can now use this description to compute the resulting spectrum with the Fourier transform. First, we look at the Fourier transform of the analog system, or system, analog signal or system. This is what we get. So this is the well-known Fourier transform. Everybody remembers? So we have this integral, and this is the typical Fourier transform correlated to the minus j omega t, where t is this continuous time variable. And here I call the c for continuous, and we have s of omega. And this omega goes from minus infinity to plus infinity. And also the t goes from minus infinity to plus infinity. And this omega here is the angular frequency, 2 pi f. Right? So the f would be the frequency in hertz, and this is 2 pi times the frequency. Yeah, so now we go to the sample signal. We compute the Fourier transform of our sample signal s times delta t of t, where delta t is the sum. Remember, I defined this train of Dirac pulses. So now we have a signal which only consists of a train of so we replace our signal by the sample signal, basically. It is still in continuous time in this way, but it only is non-zero at those sampling points. So then what we get is, instead of having this interval, we get a sum, right? And instead of having continuous values, we just have the values at the sampling points. So that's this substitution turns this integral into the sum, but the rest basically stays the same, and here we have the sampling points. Make sense? So this comes from sampling. And this is this, now the Fourier transform for the discrete time version, D for discrete. Okay. So this is then basically the discrete time Fourier transform. I replaced our continuous version with the sampled version and applied the Fourier transform. Yeah, and what you also notice is now instead of the continuous variable t, I have the discrete variable n times capital T. So this is now a major difference. Yeah, so the frequency variable now appears as, or the exponent appears as omega and t is the inverse of the sampling frequency. Right? Hence we get that omega t is identical to omega divided by sampling frequency, and we can give this in letter, capital omega. And this is called our normalized frequency. Right? Normalized because we divide by the sampling frequency. It's normalized to the sampling frequency. And this is an important point because as soon as we do sampling, it makes sense to go from our traditional frequency to a normalized frequency. Normalized by the sampling frequency. So basically this also gets rid of any physical units. Right? So for instance, if omega has the unit hertz, Fs also has the unit hertz, so the units cancel. So normalized frequency is a unitless number. It's no unit. Yeah. And in this normalized frequency, the value 2 pi represents the sampling frequency. Okay. So if this is 2 pi fs divided by fs, then all what's left is 2 pi. Okay. So 2 pi is the sampling frequency. And that means pi, which is half the sampling frequency, is called the Nyquist frequency. All remember Nyquist frequency? So that's basically the upper limit of our useful frequency range, or usable frequency range. Half the sampling frequency. So here we use the capital omega to signify that this is the normalized frequency. The capitalized version is commonly used to distinguish it from the continuous non-normalized version, if both are used. So in this case, I have lowercase and uppercase. But if you only talk about the normalized version, I will also use omega, and it's also used in lowercase omega, and that's also common in literature. So if you have a book about discrete time systems and signals, then usually you see this lowercase omega. But what it's meant is this is then the normalized frequency. Normalized angular frequency. Yeah, because there's no danger of confusion. Yeah, to convert the normalized frequency back to the non-normalized one, we simply multiply it with the sampling frequency. Okay, so going back and forth is quite easy. And to indicate that we are now in the discrete time domain, we rename our signal x of n as s of nt. So this is just a simplification. We don't need to know capital T anymore when we enter normalized domain. We just have a sequence of numbers. And then this discrete time Fourier transform becomes this. Right? We have x of n, and then we have e to the minus j omega, the normalized frequency, times n. So it's actually very simple. It's actually much simpler than in the continuous time case. And also, instead of an integral, we have a sum. It also makes it more simple. So this is the discrete time Fourier transform, short DTFT. Observe that this time index n goes from minus infinity to plus infinity. So this is something which we only can use in theory, because in practice all our signals have finite length. They start at some point and they end at some point. So this only works in theory. And there's also a version where you have a finite length summation, and this is simply called the discrete Fourier transform, or DFT. So the DFT is more practical, but this is easier to handle in theory because you don't need to care about the boundaries. So that's why you have both. For the theory you have DTFT, for the practice you have DFT. And you need to know the difference. And the difference is mainly here the summation boundaries. So that's what I said. Yeah, and another important consequence is that because n is an integer, no longer real valued like t, we get a 2 pi periodicity for x of omega. Right? So our frequency variable omega now is not really going from minus infinity to plus infinity anymore. Well, it actually does, but it repeats. It repeats every 2 pi. And that's because we have this integer valued time variable n. So Yeah, that's the first important property for discrete time signals. So here you have the complex Z-plane. And this is e to the minus j omega from the dTft, which lies on this complex, which is a circle on this complex plane. And when you look at e to the minus j omega, it repeats. When you have omega 2 pi, it's identical to 0. So this is basically the frequency domain in discrete time signals. You have a circle. Instead of a line extending to infinity, here you have a closed circle which repeats. Yeah, so we have this 2 pi periodicity because of the periodicity of this exponential function, e to the j omega. And when you look at the sum, you have e to the j omega, you have e to the j omega times n equals 1, n equals 2, and so on. And they all have this 2 pi periodicities. Right? E to the j2 omega has a pi periodicity, and so on. So all in common have this 2 pi periodicity. And that's why the result is also 2 pi periodicity. Yeah. And also for real-valued signals, the spectrum of the negative frequencies, here for minus omega, is the conjugate complex of the positive frequencies. Right? And this is again a property of e to the j omega. So if you plug in minus omega here, then you have e to the minus j omega, and that's conjugate complex of e to the j omega. Right? So, and because your spectrum, the spectrum contains of sums, again of sum of exponentials in this form, you can extend it to the sum, which means for the negative frequencies, the spectrum is obtained from the positive conjugate complex. The star here means conjugate complex. Yeah, and we need to have the property of real-valued signal, because then the coefficients of e to the j omega don't change this conjugate complex all the time. Otherwise, you would also need to conjugate complex the coefficient, and then it doesn't work anymore. Yeah, so this only holds true if we have real-valued signals, but most of the time we treat or we have real-valued signals like audio signals, image or video is all real-valued. But sometimes you also have a complex. Valued signals, for instance, in communications. Right? If you use, for instance, direct conversion receivers, usually you have complex valued signals, and then this property does not hold anymore. Then positive and negative frequencies are really different. So keep that in mind. So that means for real-valued signals, you only need to look at the frequency range between 0 and pi, the positive frequencies, because the range between pi and 2 pi is basically the negative frequencies from 0 to minus pi, and that's basically just the complex, conjugate complex version. Also have this periodicity, which means that the range of Yeah, so this is again what the Nyquist theorem tells us, that the frequencies between 0 and pi, the Nyquist frequency, are sufficient to completely describe the real valued signal. So Nyquist is for real valued signals. Nyquist theorem. Yeah, so next, sampling a discrete time signal. Right? So what happens if you further downsample an already discrete signal x of n to reduce its sampling rate? Right? This is often what we have in coders. We have a signal coming at a certain sampling rate from the sound card, but the coder wants to have it at a lower sampling rate, or internally the coder changes the sampling rate. So downsampling by n means we only keep every n sample and discard every sample in between. Observe that this results in a normalized frequency which is a factor of n higher. Right? If we change the sampling rate, we change the normalized frequency accordingly, because now we have a different sampling rate. So that's something we have to keep in mind. This downsampling process can also be seen as first multiplying the signal with a sequence of unit pulses. So now it's not Dirac, but unit, it's just once at each sample position, and zeros in between, and later dropping the zeros. So this multiplication with the unit pulse train can now be used to mathematically analyze this downsampling, and for looking at the spectra, first still including the zeros. So now the frequency response becomes like this. We have the downsampled spectrum is basically the same as before, but now we only have the non-zero ends at integer multiples of capital N. So using index substitution, this is what we did. So we can now also write the downsampling as a multiplication of the signal with the sampling function, as we did before. And in continuous time, it is a sequence of Dirac pulses. And here is a sequence of unit pulses. So here you can see it. We have a 1 if n is integer multiple of n and 0 in between. This is like we did continuous time, but now in discrete time. Make sense?
Yeah.
This is just a sequence of ones and zeros in between. Yeah, then the downsample sequence just consists of multiplying the original sequence with this unit pulse sequence. It multiplies all the unwanted samples with zero. Yeah, so this is now an intermediate signal which gets the zeros removed before transmission or storage to reduce the reduced data rate. And the decoder upsamples it by reinserting the zeros to obtain the original sampling rate. So this is then also the signal that is obtained after upsampling in the decoder, and hence the signal with still the zeros in it looks interesting to us. Because it appears in the encoder and also in the decoder. So what does the spectrum of frequency response of this signal, still containing the zeros, look like? So the downsampled signal xd can be written as the multiplication of the original with the unit pulse train. And in the spectrum or frequency domain, this becomes a convolution with their Fourier transforms. So it's multiplication in the time domain is a convolution in the frequency domain. So we just need to have the Fourier transforms of the two. The Fourier transform of the unit pulse train is a Dirac impulse train. Turns out it's a Dirac pulse train. But that's not so easy to derive. So we just apply a simple trick to make it mathematically more easy and get converging sums. So we start in the frequency domain and have to guess what the Fourier transform of the unit pulse train is. We get Dirac pulses at frequencies of 2 pi over n times k, where we have a fundamental frequency of 2 pi over n, and its harmonics. So why 2 pi over n? You have to guess. You have a guess why I came to this guess? Yes, exactly. So 2 pi is the original sampling rate. We downsample by n, so the new sampling rate is 2 pi divided by capital N. So this is your new sampling rate. And since we have a non-sinusoidal signal, we have harmonics. Right? Only sinusoids have no harmonics. Everything else has harmonics. Actually, multiples of fundamental frequency. So that's why this makes sense. We have 2 pi divided by n, and it's harmonics. Okay. So this actually also includes k equals 0. Why does it include k equals 0? What does k equals 0 refer to? What frequency? It's frequency 0. Right? So what is frequency 0? How can you interpret frequency 0? And it's DC. Have you heard about DC?
Yeah.
Direct current? So that's the constant non-changing part. So why do we have DC here? Remember we have ones. How do you compute DC? If you have a signal and you want to know how much DC do you have in your signal, how do you compute it? Yeah, what? Yeah, exactly. Average. So if you have, for instance, a signal from a microphone, you just compute the average, and if all the plus and minus cancel out, then you have no DC. But if you have DC on it, then you will see that the average is non-zero, right? Meaning some fixed voltage is on the signal. So DC is computed by computing the average. So what's the average of our Dirac pulses? Unit pulses. We have unit pulses. What's the average? Well, it's something positive, depending on how far you go. It's not 0, because you only have positive pulses, but not negative ones. So you have DC. Makes sense? So that's why you also have to include k equals 0. So up to where will you go? What's the range of this index k? So we know we start at 0. What's the upper end? What do you think? How far do we need to go? What about k equals n? Yeah, exactly. So k equals n, and this cancels, and you have 2 pi, and that's identical to 0, right? Because of the periodicity. So k equals n minus 1 would be the upper limit. Right? That's the last one we need to compute. So the range here is k equals 0 to n minus 1. So this is then our guess. We have our Dirac pulses at these positions in frequency. Right? And we have some factor here, which turns out to be true later. It doesn't really matter so much yet. So this is some factor. And then here's the sum for k equals 0 to n minus 1. So this is the k range here that we use. So we have those capital N spectral entries. So this is now our guess. And now we need to apply the inverse Fourier transform to see if this is really the unit pulse train. Okay. So we apply the inverse discrete time Fourier transform. And this is the inverse discrete time Fourier transform. You all remember? So it goes from 0 to 2 pi, just from 0 to 2 pi because of the periodicity. Here is our guess spectrum for the unit pulse plane, and this is the inverse Fourier transform curve e to the jn omega. Right, and this also comes from the 1 over 2 pi comes from the inverse time Fourier transform. Makes sense? So now we get something, and what we get should be the unit pulse trace, if you're right. So it's actually not too difficult to compute, because here we have just Dirac pulses. So here, this is our n Dirac pulses, which are just inserted here. And then we can compute the integral here. And what's left from this integral is just those sampling points, basically. So here, this Dirac samples this function. You see that? So we only keep the values of this function at these frequency points. It's basically sampling of the frequency domain. So here you can see the result. The sum is still there, and what's left from this function here are these frequency points. So we sample this function here at those frequency points, and the 2 pi cancels here, and what's left is just this 1 over n. So now you know why I had a 2 pi here, because it conveniently cancels. So this is our formula. Yeah, so what do you think? Is this a unit pulse train? How do we know? It looks like complex oscillations, right? This is the sum of complex oscillations. And yeah, maybe they sum up to a unit pulse train. We don't know yet. So we have to prove that this is indeed our unit pulse train. And to do that, we can just look at the sum. And we see that this is a geometric sum. Do you know geometric sum? So this is the general form of a geometric sum. You have some constant, and then you have the sum index in the exponent. And this sum goes from 0 to n minus 1. So here I dropped this 1 over n for convenience. And you see here, we have this k in the sum, and here the k is an exponent, and the rest is our constant c. And I'm omitting this 1 over n for the moment. Yeah, and if we have such a sum, we can get a closed form solution, as you can see here. We just write the sum multiplied with c, and the result is just a shifted index here for the sum. And that means if we compute the difference, we just keep the last and the first entry. The last of the second sum and the first of this first sum. Can you see that? So we take the difference between those two, and you see here, these indices are shifted by 1. So most cancel, most of those sum entries cancel, except for the last one of this one and the first of this one, because they don't overlap. So we know that this is true, and then we can just factor out s and bring the c minus 1 on the other side, and this is the result. So this is our closed form solution for the sum. And now we can just replace c by this e to the j 2 pi over n times n. And we have our solution. Yeah, so this is our closed form solution for this. And now we can check. So this sum must become n, because I dropped this 1 over n, for n equals mn. Right? And we can check it by simply plugging it into the sum here. So here this becomes mn. That means here capital N cancels, here capital N cancels, and we just have e to the j 2 pi times some integer. What is e to the j 2 pi times some integer? 1. Yeah, it's always 1, right? So we have 1 minus 1 is 0, and 1 minus 1 is also 0. So what's the result? What's 0 divided by 0? Yeah, undefined. Right. So that means here we are stuck. Now we can look at the left-hand side. So basically, left-hand side. Yeah, this piece. So now we simply plug in the same on the left-hand side, and this n cancels. So again, we have 2 pi times some integer. So again, we know this is 1, and the sum over 1s is how much? Yeah, it's n. Right? We have n 1s, so that means the n sum is n. And this is right? This is what we want. We want the sum to become n. Oh, that worked. So now we just need to check for the zeros. So for n unequals mn, we need the sum to be 0. And here we can now use the right-hand side which we just occupied. The denominator is unequal to 0, and the numerator becomes 0, and hence the sum indeed becomes 0. So this is this one up. So here, when n unequal mn, then we cannot cancel this. Right? And that means this expression is not 1. And that means not 1 minus 1 is also not 0. Right? But when we plug it here, if this doesn't hold, we cannot cancel, but still it's multiples of n. Right? So this becomes 1 minus 1 is 0. Make sense? So indeed, in between the ones, we have the zeros. Yeah, so now we know that our unit pulse string can be written as the sum of these complex exponentials. Which is kind of surprising because they are oscillations. Some of oscillations now become a period of modes. Yeah, now we can use this expression to compute our Fourier transform. Here, plug it in. So this is now our sample sequence. And this expression, this exponentials, has the advantage that it gives us a nice Fourier transform. So here comes the discrete time Fourier transform. So here's this is the sum from the Fourier transform. And this is the Fourier transform kernel, remember? So this is part of the Fourier transform, and this is now our sampling chart. And now you see that it nicely fits to the Fourier kernel. We can have an explanation. That it nicely fits to the Fourier kernel. We can have an explanation here, and we have an explanation here. So we can put them together and add the exponent, which you see here. Those two exponents together. So I have the minus in front of all of them. So I'm changing the inside. And I could factor out the n here together. Can you see it? Makes sense? So now I can also draw out this inner sum to the outside. And you see this inner part here is the Fourier transform of x, but shifted transforms by 2 pi over n times k. Right? And you have not just one Fourier transform, but n Fourier transform, n shifted Fourier transforms of your signal. Right? So for k equals 1, we have the original Fourier transform of your signal x, the unchanged one, but for higher k, you get shifted versions, which now appear in this spectrum. These are spectral copies or ADSP copies. So this is what you get. Here you have the spectrum, and you have multiple spectra which are shifted. You not only have the original, but only have shifted versions, multiple shifted versions of the spectrum, so-called ADSP copies. So this is the main result of. So it's shifted spectrum. Also observe this 1 over n, which means the original spectrum is now 1 n smaller, and also the spectral copies are 1 n smaller, which means the total energy stayed the same. It didn't change. Yeah, so here you have the original spectrum, for instance, and now you see multiple spectral copies appearing in the spectrum because of this sampling. And they appear at positions 2 pi over n, 4 pi over n, and so on. And these are the ADSP points. So this is basically the main result. Yeah, questions? So this is what you should keep in mind and what you should remember when you do the sampling and get spectral copies. Okay, so thanks for your attention and have a nice day.